Atoms and molecules, so I think this is big enough so you can see where you are, but if you need to move forward, feel free. And so there's kind of three main questions that I want you guys to be able to provide me with good answers for at the end of today, and we're going to do a few activities to hopefully clarify this so you can give me some real responses to hopefully show if you know this stuff or not. But really, as you're going through all of this, pay attention to these ideas. So what actually is an atom, what's in it, what's the size of it, and so on. Then why do atoms come together and form bonds? Because obviously we have all these individual atoms, but they're doing something interesting in order to make us and to make the world around us. So what's going on, what's driving that? And then the last thing is, how do these different types of bonds, or how do the way that atoms interact with each other lead to different properties that we observe? And so hopefully we'll go through all of this today. And I'll give you a sort of foundation that you can start to motivate this stuff and really, hopefully, get kids interested in this and also have an understanding of it yourself. So,
wait, what was that last question?
I'll give you this PowerPoint presentation too, so you can get it all. But the last question is, how do different types of bonds affect the properties that come out? All right?
Are you going to give us a description of who you are?
Oh, I'm Gerrick Lindberg, and I am a postdoc in Greg Voth's group. So I think his group has been the people you've mostly interacted with. I guess Aaron Dinner is another professor here, but Greg has a large group that does theoretical chemistry. And so we use computers to try and take all this kind of information that I'm about to tell you about, put it all together with the appropriate physics, and then try to understand what's going on. And so I'm really a stat-mech person, so I use kind of statistical methods to try and figure out what's going on.
So did you go to school here, or?
I did not. I grew up in Oregon, and I got my undergraduate degree in Oregon. And then I went to Boston University, where I got my PhD, and I've been here for a couple of years now. All right?
What part of Oregon?
I grew up in Corvallis, so kind of, I don't know, in between Eugene and Portland.
Oregon Trail?
Yes, that is a thing.
What kind of dog do you have?
I have a mutt. She is a Beagle Terrier mix. We're not really sure what she is, but that's what she looks like. Did you write that down?
Yes.
Okay. So, I think the first thing when you start talking about atoms is just kind of where did this idea come from? And I think now we're so ingrained with this idea of atoms, you know, at the smallest scale, when we're talking about chemical properties, there's something there that you kind of have this ingrained in your mind from a very early age. But if you start to think about that, these are things that we don't see. We never really interact with individual atoms. So where did that idea come from? It's a pretty amazing, pretty striking thing that's so different than the way we interact with matter around us. You know, if I take a little bit of water and keep splitting it up, I can always have water there. I can never break it down to an individual water molecule that I can observe, or an individual oxygen atom would be even more ridiculous or incapable of understanding, right? So where did this original idea came from? And so if you go way back, there's this guy in Greece who, he didn't even have any observations. He was just thinking about, I think, a block of granite. If you just take a block of granite and break it into two pieces and just keep breaking it down, he came up with this idea that it's ridiculous to him to just think of it continually breaking. You must reach some point where you can't break it down anymore. And so we see the foundations of this kind of atomic theory or the idea of a discrete matter theory that come out from very early philosophies. And so this idea kind of rumbled around for thousands of years, although predominant thinking, like Aristotle, still thought matter was continuous. He thought if you took a block of something, you could just keep breaking it down indefinitely, and it would always be that something, just two pieces of it. So the predominant theory was this, but there was this idea that it would make more sense if you reach a certain scale where you just can't do it anymore. There's got to be some lower limit. And so this idea kind of rumbled around for a long time, and then, you know, we had the scientific revolution, and we had these really amazing experimentalists developing all these neat ways of observing the world around us and so on. And so then we started to see theories about this kind of stuff. And so John Dalton came up with this idea that elements, so if you can isolate something that in itself seems unique in some way, so if we have carbon, so like diamond or graphite, or oxygen, O2, these things are are composed of discrete particles called atoms. And these atoms are indestructible by ordinary means. So this thing, an individual oxygen is an oxygen, and if you break it apart, well, it's very difficult to break it apart. And if you break it apart, it's not going to be an atom anymore in the same way. And all atoms of the same element have identical physical and chemical properties. So if we have an oxygen and it is an oxygen, it's going to behave, every oxygen is going to behave in a similar kind of way. So we can use this as a way of categorizing the matter around us and really understanding what's going on. And then the last thing is these things are going to come together and do something interesting. And so you can see here that we've essentially kind of restated the stuff from the first slide with a few more words, but we have elements, and they are composed of atoms. This atom is the important thing that we're going to use to categorize what goes on with matter, and they come together to do some really interesting things. Okay? So, I think now this leads us with, we have this idea of there being something that's indistinguishable, that we can break it apart, we can categorize matter in terms of these individual little particles. But what are these particles? What defines them? What are the important aspects or characteristics of them? So, what do you guys think? What are the building blocks of an atom? A little louder.
I'm going to suggest electrons in the next slide.
Good guess. Electrons.
Neutrons and protons.
So we have a nucleus. So we have electrons, a nucleus. You said
Protons.
neutron and proton.
Yes, I
Yeah.
did.
And so we've pretty much put everything together right there.
No,
So we have three things, and they're kind of in these two different regions. We have a
We're missing
nucleus.
something. What are we missing?
What are we missing?
Yes.
I don't think we're missing anything. So we have electrons, protons, and neutrons.
We're missing something. I'll know what the something
You let me
is when I
know.
see it.
And then these things are composed in the or oriented in these different regions. But so these are the important things we want to know about the components of an atom. And then what do you think are maybe the most important characteristics of these particles? So if we want to describe these things, what are we going to say? Yeah, so charge is one important thing. So protons and electrons have charge on them. And that charge is an important characteristic of how they behave. Is there anything else that you think is important about
Size.
the size? Yes, the size. And in particular, what about the size? I guess size, and then there's one other thing I guess about. So electrons are tiny,
Yes.
while these two are much larger.
Yes, yes.
And then there's another thing that usually we tie to size as well.
Wait.
Mass, yes. So the last thing are these important characteristics. And so if we go forward one more slide, we can see that these things were uncovered at different time periods, and you can see the two that have charge associated with them were discovered much earlier than the one that doesn't have charge. A neutron doesn't really interact with things, and so uncovering that this thing existed was actually quite a challenge, and that's why it happened about 30 years later. And then you can see the masses are very different, where proton and neutron are essentially the same. An electron is much, much lighter.
Negative. Electrons negative, protons positive, neutrons neutral.
Correct. The charges, yeah. And then again the charge down here, and then symbols. So those are kind of the three important things we want to, the three important things in an atom, and then they each have three kind of important distinguishing characteristics to them that cause them to behave and interact with each other in these very important ways. Okay? So we kind of already answered this because you were on top of things, but how do these things actually arrange inside of an atom? So for example, we know electrons exist. J.J. Thomson was able to isolate them. He knew they existed separate from everything else. The same thing happened with protons. They isolated them separate from everything else. Now we're going to say that matter is composed of these things. How did these things actually come together in order to make matter? And so there are a number of theories. So here's the Thomson model. So if you remember J.J. Thomson from the previous slide, he found the electron before any of these other subatomic particles were discovered. And he came up with this idea that's called usually the Thomson model, but also the plum pudding model, I guess, because he's English and it's green in this coloring. This idea that you would have electron particles that you would smear out. You probably have something similar for protons that you would smear out, so you'd have a positive smear charge around. And so we smear all this stuff together and we end up with the matter that we're used to. And then there's another model that came around a little bit later called the Bohr model. So this would have been probably just 10 or 15 years after this. And so this is probably one that we've all seen more than we should see. Like if you watch The Big Bang Theory, you'll see this kind of in between every segment that they have. We have this thing in the middle, which is the nucleus. So that's where those heavy particles are. And then we have little electrons orbiting around that nucleus. And then we have the cloud model, which you don't see so much of, but that's another idea, right? Where we have in the center a nucleus that's very small. And then we have this smeared out electronic charge around it. And so, do you guys know anything about any of these models? Do you have any preference for which one might be more scientifically correct?
The Bohr model, I think that's just because what I've done.
That is very intuitive, yeah. Any other thoughts on this? So when we go down to this really small scale, things get confusing because this is actually a realm where quantum mechanics becomes very important. And it turns out that electrons are so small, they're so light, that they are actually more of a quantum particle. We should think of them in terms of quantum mechanics, not so much of our everyday experience like a ball bouncing or a planet orbiting around a sun. And so I realize this is confusing, and I realize the reason why we would stick with this kind of planetary model for so long, because it's just intuitive. It makes sense to think of the heavy thing in the middle and everything else orbiting around it. But what's really going on, if you take experiments and you look at the way that electrons interact with things around them, they actually do smear across the atom like this. So you really do have an electron, one electron, that occupies this big wide area of space. Even though the mass of it is more than 1,000 times smaller than this thing in the center, the electron behaves in these crazy, strange ways of quantum mechanics that cause it to distribute itself across this. So this is the kind of picture that, at the end of the day, you want to picture with an atom. And I realize that it's not intuitive. You can't think of the world in terms of quantum mechanics like this, because it just doesn't connect with our physical observations of the world around us, right? If we throw a ball, it doesn't make sense to think of that ball smearing out in space all over in front of us. But this is the way that particles behave on this small scale. And so I think as you're teaching this, or as you're thinking about it yourself, you want to keep these two pictures in mind. So this one is useful for kind of imagining where things are in space, what's going on. But this is the kind of picture you want. You want to have this idea of this thing smearing out around the atom, occupying these different spaces all at the same time.
Okay. In the cloud channel, how would you explain the different shells?
So the different shells will come up, but these are things called orbitals.
Okay.
And so it's just going to be different places in space where it can smear out. Okay. So, as chemists, as physicists, when you're talking to students about these ideas, you want to keep this idea in mind. So you want to, I think, have them familiar with this so that as they move on in science, they'll at least be accustomed to this idea. Okay. So we have this basic understanding of what an atom is. We have the three main things that show up in each of them, right? We have the nucleus that contains protons and neutrons, and we have electrons there. But there's all these different elements out there, right? So what is it that makes one element different from another element?
Numbers of electrons, neutrons,
I can't hear you.
protons involved.
So she said numbers of electrons, neutrons, and protons.
Amount of certain.
So there's one of these things in particular that's important, particularly for the way we categorize, what separates hydrogen from helium and what makes up the periodic table. So what is the one?
Mixture of elements that can.
Not a mixture. There's just one of these things that's important. What is it?
Is it what?
Not electrons.
Mass.
Protons. So we're going to categorize these things based upon protons. And so atoms contain all of these things, but the proton is what defines hydrogen or helium or lithium. So hydrogen has one proton, helium has two protons, lithium has three, and so on. That's the way we've decided to categorize the periodic table. Yeah.
All the elements on the
All of them. You just keep marching through. Each one has one more proton.
Wow. So hydrogen has how many?
One.
One, and helium has two, and lithium has three.
Yeah, and you just keep going, and we're going to add one proton to each one as you go along.
Aren't you also adding one neutron?
No.
Not
We'll talk a little bit about that, but no, you're not. So that's how we've labeled that thing. That's how we've labeled atoms in the periodic table. And this is a useful way of kind of breaking them down into the way they interact with others. If we know how many protons there are, for the most part they interact in ways that are very well characterized and very well describable between each other. Okay. So, number of protons, and sometimes this is called the Z number. I find this annoying because I can never remember it, but if you're reading a textbook, oftentimes the Z number will come up, and that just means the number of protons. I know, that would make so much more sense. Okay, so here we have a periodic table, just to reiterate this. So up here, hydrogen has a 1 next to it, that's 1 proton. Helium, 2 protons, and so on. Lithium, beryllium, boron, carbon has 6. And you can just keep going all the way down here to the bottom. For example, fermium has 100 protons. All we're doing as we march across this and down this is just adding another proton, and then that's a useful way of segregating these things so that we can understand the way that they're going to behave. Okay. All right. So we understand what it is that separates these things, the way we've decided to label them. So that's protons. So what about neutrons and electrons? How do these things fit into this whole equation? So first of all, we're going to talk about neutrons because it's a little bit easier to deal with. And so the way that we've decided to build up the periodic table and to kind of describe atoms depends very sensitively on the number of protons. If you go from hydrogen to helium, those are very different things, and they always behave in very similar ways. If you change the number of protons, it doesn't actually change things, or if you change the number of neutrons, it doesn't actually change things that much. So, for example, hydrogen, the most common form of hydrogen that we interact with 99.985% of the time is H1. So that means there's one proton and no neutrons in it. But there is a small amount of deuterium that exists naturally in nature. 0.015% of hydrogen is deuterium, which means it's one proton and one neutron. And so if you look at this naming scheme here, down here we have that same Z number from before, and then up here we have the total number of heavy particles in this atom. So we have one proton, and then we have a 2 up here, which means there's one proton and one neutron. So you have to subtract them to get back the number of neutrons.
How do you know it's a neutron, not an electron?
Because electrons are light, remember?
Okay.
So these are only heavy particles, things that contribute to the mass.
So the proton is usually at the bottom, is that what you're saying?
Yeah, it's always at the bottom, and this
So
kind
the
of
top number
is
is the
number of neutrons plus protons.
number of
Ionize.
neutrons plus protons.
Yes. Okay.
One proton and 2 neutrons then, the last
2 neutrons plus proton.
plus 1 proton.
Yeah.
Okay.
Okay. So this is deuterium, and then tritium is also a thing, and so that's 3 total. So then we'd have 2 neutrons there.
One
Yes. I almost said it wrong. But then down here, the natural abundance, I've put 2 dash marks. Does anyone know why I would do that? So we can definitely make this. You can see this in certain circumstances.
Well, you're talking about natural abundance, not what can exist.
Yeah. And so this has existed though.
Yeah.
So what would happen? What would be going on that would make it so that this wouldn't be something that we observe all the time?
It would not be stable.
Right. It's not stable. So you can make lots of crazy things. So like down here I've said H4, 5, 6, so on. So we can have these other isotopes that can occur, but they're unstable. So they're going to go through some nuclear reaction. They're going to break down into probably hydrogen and deuterium. And so these things just won't be around in nature. So you see these things in nuclear reactors or something like that, but over time they'll break down and not be actually present in nature around it.
When you say they're not stable, are you saying that because there's no proton number at the bottom?
No. So all of these, there's a 1 down here that's implied.
Oh.
And so they're not stable just because of the way that nature works. For some reason, when you put 2 neutrons and hydrogen, it's not stable. And that's really not an easy question to answer.
Okay.
Why that is,
Thank
but
you
it is.
for saying that.
Yeah. Okay. So we talked about this, I guess, on the previous slide. But so we have all these isotopes. Some isotopes for certain elements just happen to not be stable. And so some of them we can make and they'll just fall apart really quickly. Some of them we can't even make. Some of them are theorized to exist, but no one's been able to make them yet. And so there's, I think, a lot of interesting things going on here. But the most important thing is just to understand that neutrons are there. They affect the stability of atoms. But really the property of a hydrogen doesn't depend too much on these other things. Okay? And so the last slide, yeah.
I'm sorry.
No problem.
We're going super duper fast.
I know.
What is an isotope again?
So isotope refers to the range of possible neutron values that you can have in an atom. So we have hydrogen with 1 proton and no neutrons. So that's one isotope. The next one would be adding another neutron to it. And so as you add neutrons to it, you get different isotopes of an element.
Yeah.
She said the range of possible neutrons.
Yeah, all the different possible neutron counts that you can have. So here what we're doing is looking at the possible isotopes of every different atom. And so here, there's not much to take away from this other than to see that, so down here we have protons, up here we have neutrons, and you can see there's this range of acceptable mixes of numbers of neutrons and numbers of protons. So across here you would be seeing all the different isotopes of a particular, up this way, because that's a fixed proton count. You'd see all the possible isotopes for a certain element. And then you can also see, I'm sure this is hard to see, but up here in black is stable. And so down this diagonal here you can see there's a black line that kind of forms, and those are the stable isotopes of particular elements. And so you can see as you veer away from that, you get unstable ones that will break down very quickly. But in this core, at a slope that's slightly greater than 1, so in order to get stable elements, you're going to be adding a few more neutrons than you have protons. I think the number is about 1.7. I don't remember that. I'm not sure about that. But you have slightly more neutrons than protons in stable elements. And so we know for hydrogen There's no neutrons there, so it starts at 0, and you just add in slightly more neutrons as you go along in order to make stable elements. And again, this is a confusing, not straightforward question to answer, but it's what's come out of nature.
Okay. At some point in today, can you discuss what half-life is, and this might not be the time?
Maybe we could talk about that independent from this.
Oh, okay.
I mean, unless everyone's interested, but we could talk about that. It's not something I planned on.
Oh, okay.
Okay, so, talked about protons, neutrons, electrons. So, I'm going to ask the same question essentially that I asked before about, we put the periodic table together in such a way, we've named elements in such a way that corresponds to protons, right? So the one here, hydrogen, tells us how many protons there are. So now, what can you tell me from the periodic table about where electrons are? Do we know that? How does the periodic table relate to how electrons exist in atoms? You're nodding. So.
Yes, I am. Okay, the hydrogen and helium have the smaller shell that only has 2. And so therefore you've got 1 position filled, 2 position filled. That's why there are only 2 on that row.
Right.
So each row you have a different outer shell, and you either fill it with 8 and 8 and then, I don't know, maybe 16?
Excellent. It's
Okay.
not 16, but, yeah, it is 16. Yes, yes.
Okay,
Or
can you
18,
explain
sorry.
that to us?
I'm cheating. I'm reading the book Disappearing Spoons. So
I
I'm
see.
saying,
Okay. So what she's saying is we've put the periodic table together in such a way so that we can see when we're filling up orbitals. So at the top here, at the center, we've filled up orbitals in such a way that the hydrogen to helium ends up with a filled orbital. I think if I move on, this will be a little bit easier to explain. So here we have the s block. So we've named these orbitals in such a way, the places where these electrons are going to sit. And so here we have s block. So we're going to be filling this orbital with electrons. And when it's filled, then...
Again.
Yeah.
Okay.
So I'm hopefully explaining what's going on with
Back up a little
electrons.
bit. You said orbitals. That's where that's where the electrons are going to sit. That's
Yes.
what those are called. Okay.
Yes. So an orbital or a shell, those are 2 synonyms. These are the places where electrons are in atoms.
Okay.
And so these different orbitals have different shapes. And so we're going to assign those different shapes different names. And so one shape is S, which is just a sphere. Another shape is this kind of dumbbell thing, and I'll show a picture in another slide or two. But we call that P. And then D is this other crazy thing that comes out of math that's a little bit tough to picture, and I'll show you a picture of it. But we've segregated these things because they have different shapes that come out of the basic physics, okay? And so, as it turns out, atoms are most stable when they can fill up all of these shells, okay? So here, at the top, we have hydrogen and helium, and it's filled this particular shell. And this is very stable here.
Those are inert.
And if we go down a level, we have an s orbital here that we can fill up, and then it has some very similar in energy p orbitals that it can fill up, and then once it's filled those, it's very stable again. And so the periodic table is arranged in such a way so that we can see there's filling across this row, and if it can get to some electronic configuration that looks like it does over here, like this column, it's very stable. And so that's why the periodic table is arranged in this way. So we have orbitals that occur around these atoms, and if you fill the orbitals with electrons in order to get over to here, it's very stable. And so we call the atoms, or the elements that occur in this column, noble gases. So this is hydrogen. What are the other ones? Or not hydrogen, sorry. This is helium, neon, krypton, and so on. Argon, neon, yeah. So all these noble gases go down here, and these are very stable. They don't react with anything for the most part. And so what we're going to find out as we move along is that the other elements, as you move over to the other side of the periodic table, are actually trying to take on characteristics to be like the noble gases. Okay? And so I hope that makes sense, why the periodic table is put together this way and what the periodic table tells us about electrons in atoms. Does that make sense? Did I help? We're going to talk about it a little more too.
A little bit.
All right, so.
You know what, to be honest, I
Yeah.
really like what she said about when the periodic table was up there and you explained about the neutron, the amount of neutron and the amount of protons. I completely understood that. But then when she was explaining what electrons were on the periodic table and you didn't reiterate that, I didn't get it. I didn't get what electrons are on the slide before.
Okay.
Perhaps I'm, yeah, right there, like,
Yeah,
when she
so,
was explaining.
so I think what's confusing about this is that, so what really defines hydrogen is there's one proton. So we can have different numbers of electrons there. But what the periodic table, the overall shape of it tells us is that there's certain electronic configurations, so numbers of electrons that different atoms want in order to be stable. So a hydrogen with no charge on it is going to have one electron. But that's not actually stable. It has two spots, it has two seats in its orbitals around it, and it's going to want to fill those up in order to be helium-like. And so we've arranged the periodic table in such a way that you can see what they want to be like. They want to be like these elements over here.
Which are stable.
These are all very stable,
So
yeah.
whereas the 18, 88, all of those, they are stable.
Correct, yes.
But the ones where it says 1 and 1A, all of those are not stable.
Yeah, and so the
And
ones...
those are all stable because they have electrons?
So they all have electrons, but they've filled up their shells with electrons. And so we're going to talk more about this. So I'm not done with this subject by any
Do
means.
they reproduce the electrons, or they make them? Or?
So what they're going to do is bond with other atoms in order to share electrons.
Got it.
Okay? I'm not done. We're going to keep going with
Okay,
this. But if you understand the periodic table, you understand that what we've done is arrange this in order to see where these different orbitals are and how they're being filled as you move across it. Okay? All right. So there's all these names and principles associated with how we're going to put electrons in atoms and so on. I think when you get to be an undergraduate, you have to memorize these things. They're not really that important though. What's important is that there's all these spots in orbitals for electrons, and you want two of them in each orbital. Each orbital has two spots for electrons, so it's just like sitting on a bus. There's two seats, you can fit two people in a seat, and it's actually happiest when there's two people, so if you're riding on the bus, you'd like to have someone there with you, right? And you can't put more than two people in. I assume you have someone in your life that you love.
Okay, yeah, but no.
Go back one.
Yes,
Okay.
okay, you see there it says, this is called the Pauli exclusion principle. Is that Lionel Paulus?
No, Paulin. You're thinking of Linus Pauling. No, this is Wolfgang Pauli.
Okay.
So he came up with this idea that you can only fit two fermions into the same state, or same orbital.
Okay.
And I think the details of that, I mean, you can touch on this when you're teaching middle school schoolers about this. Obviously, there's deeper physics here that's important.
Okay.
But the important idea is that you just have two electrons per orbital.
Okay. Okay.
All right? And so we have our happy woman sitting in a seat. Presumably, she has a significant other or somebody or a child that she likes, and she would be happy sitting next to them. You put anyone else in this seat, it's just going to be too crowded, and they're not going to like it. Okay? So, I promised you before that I would show you what the orbitals look like. So up here we have the s orbital, so that's the sphere. And then if you go, to the periodic table where you had all those other elements appear, the p orbitals appear. So you have 3 p orbitals. So we have 6 more electrons that can fit in, and you can keep going on. So then you drop down a few more rows, and the transition metals appear. And so that's all these d orbitals coming into play.
You said the d orbitals had something to do with a complicated math thing.
Well, all of them have something to do with complicated math, because what we're doing is solving for where the electrons can be. But it turns out that the solution to the complicated math is pretty simple. We get a sphere up here. We get a dumbbell kind of shape here, so not too complicated.
Yeah, okay.
Then we get this kind of three-dimensional clover-like thing here. We get the donut, the 2 spheres on it. These just happen to be solutions to where the electrons are in these different orbitals.
And these are their clouds.
Yes.
Okay.
So these are the clouds, these are the shells, all the same kind of terminology is describing these arrangements of electrons around it.
Okay, and the cloud would not necessarily just be 3-dimensional.
No, these are
They're all
three-dimensional.
dimensionals. Okay.
Yeah. All right.
Mm-hmm.
So, what in undergraduate general chemistry and I assume in middle school, what you really want to focus on are these first two. So these are the top of the periodic table. And so this is where we're filling that first s orbital, which we saw over on the left side of the periodic table. And then as you drop down another row for carbon and all of those kinds of elements, the p orbitals. And these are the way that these affect electrons. And most of the atoms we deal with is what leads to life and so on. So I think if you have a strong understanding of these, that's going to set you up well for moving forward in chemistry. So this is where I'm going to focus the rest of today, and where I would recommend you guys focusing in middle school and people focusing even as undergraduates for the most part, because it simplifies things that you just have to consider these 4 kinds of orbitals. And it leaves apart a lot of complexities that come about with d orbitals and how electrons are going to spread out through them and so on. Okay? But they do exist, and you can see from the periodic table where those 10 slots across the transition metals come from, because you have these 5 orbitals with 2 spots each.
Okay, I've got the piece of 1. What are we got piece of 1?
So another way you could label these, so all they're doing is telling you about different axes that these orbitals can lie across. So another way you could label this is a piece of X, piece of Y, and a piece of Z.
Okay.
So it's telling you there's 3 independent or distinguishable axes that go through the molecule, and these p orbitals lie across along those 3 different ones. Okay? All right. So I think we've covered an atom pretty well. We understand what's in an atom, how things are distributed, what the important characteristics of these different things are. So the first activity that I had planned for today is to hopefully get a better understanding of the scale of an atom, and to understand really how the nucleus size relates to where the electrons are in this thing. And yeah, so hopefully we'll get something out of it. So I'll, just because we don't have a lot of time today, I'll talk through the beginning just to hopefully make sure that everyone is on the same page. And then there's a few problems for you guys to answer. Okay, so we've already talked about how atoms are the fundamental building block of matter. Yes, thank you. And you can read through this introduction. But in particular, like I said before, what I wanted to create an activity to understand is what is the scale of an atom. So for example, the first part of this, which I actually work out for you so you can kind of see how to do the subsequent ones. The first thing is, if I were the nucleus of an atom, where would my electrons be? Where would be the outer edge of the electrons? And so if you go down to how does the scale of an atom relate to some everyday objects, so you're going to need to go through the first part, but just kind of getting you guys working through the math and what you're going to do in this problem. So what I did is I asked, so if I had a nucleus that is Gerrick sized, so my size, how far out will the electrons be? And so the math is actually pretty easy, I think, and I have it all spelled out on the paper. But so if I think of me as a particle, and so I can just say that my radius then would be half of my height. I think that kind of makes sense, right? So I have some height, I'm 5'11", 5 feet, 11 inches, and I'm going to say the radius is half of it. I'm not going to be too greedy. All right? So then this means that my radius is about 35.5 inches. All right? And so now we're going to ask the question, how far out would the electron clouds be if an actual atom had this kind of nucleus, okay? And so, do you guys have any guesses? How big do you think an atom? What do you think the scale of the nucleus versus the clouds around it is? Be bold, just throw a guess on it. What do you think it would be?
You wanted to know how far out they would be from it?
So first of all, would the number be smaller or larger than this?
Much larger.
It'd be larger, yeah. And how much larger?
I'm going to say 10 feet just to go.
10 feet. Okay. Any other guesses?
Is it twice the size?
Twice.
That was the same as
So twice the size, about 10 feet, something in that range. Okay. So the way that we're going to actually go about doing this calculation is we're going to take a real atom. So in this case, oxygen. I've given you the parameters for oxygen. And we're going to look at how my height, if it were scaled by the size of an oxygen atom, where the electrons would actually be. Okay? And so what I'm going to do is take my radius, as I've defined it, and what I'm going to do is scale it by a ratio of the appropriate oxygen value. So are you guys familiar with ratios? All right?
Yeah, we know that much.
And so if I have the radius of an oxygen, and I have the radius, sorry, radius of an oxygen, it's not anything. It's either the sound or the horrible writing.
Yeah,
I'm sorry.
The horrible writing will take.
Yeah. Okay, so I have the nucleus, and I've already said that we're going to look at an atom that has a nucleus my size. And then I have the total radius. How would I put these two values into this formula to extract what I'm after, to extract the total Gerrick atom size? Any guesses? So it's a ratio, right? So we're going to put these two values in here
The
somewhere.
the oxygen also
Right. So I'm going to put the radius of the nucleus down here, because this is my nucleus. So I'm going to have the oxygen nucleus. And I'm going to have the atom nucleus up here. And then I can just take all these numbers, which I've given you on here, and we can multiply them out and see how big this atom would actually be. And so the first problem is actually calculating this ratio. Okay? So what you're going to do is take the atom nucleus and sub it in here. So what does that end up being? So that is 6 picometers. And so I describe on here what a picometer is. And then down here, did I have that right? Oh, sorry, I'm backwards.
So isn't it just the radius on the left that would be 6? It's not the atom nucleus. Oh, it says atom.
Sorry, this is the atom radius.
Oxygen atom.
Yeah, the oxygen.
Sorry, you guys should have caught me on that.
What is the radius?
What?
The atom radius?
Yes. So this is the overall size of the oxygen. This is the size of the oxygen nucleus. Okay? And so, of course I'm going to blame you. I'm not going to
I was
take the blame.
just testing you guys.
I'm on stage here.
We do that to our
performing.
kids all the time.
So down here we have, a picometer, and then up here we have the. Did I have this right this time?
Wait, the oxygen nucleus 6.05.
Yeah. Wait a minute. The-
You're right. Okay.
But that's
So-
the radius.
So on the bottom it's
Oxygen nucleus has a
6.0.
radius of 6.05.
There you
FN.
Now you're paying attention. So FM is a femtometer, and then up here we have
So it's 6.0 over 6.05.
Yeah, and then it's important to know what the little p here and the little f mean, and those are in the first problem. Okay. And so if we put this number in here, we put this number in down here, we multiply this all out, you end up with 35,000 inches.
And the radius. Sorry. Jeez.
No problem?
Oh my gosh, that was rude of me. The left, the radius,
Yeah, this is just this number,
That
so the
is-
radius of Gerrick.
is that 35.5 inches?
Yeah.
So
And
that
so-
goes there.
And so I've spelled out this math here.
And are you gonna put that over 1?
Over 1.
Yeah, how did you calculate that out then?
I'm not sure what you mean.
Or are you dividing it and then multiplying it?
So I have the Gerrick radius,
Mm-hmm.
and then I'm multiplying it by this and dividing by this.
Oh, okay,
All right?
yeah.
Gerrick radius is always 35.5?
I'm not growing anymore.
Oh,
Why did you multiply the picometer 65 times 10? On the back?
So this is a metric system, right?
Okay, so you're using the metric system.
So the metric system would be something you want to cover before getting to this point. So
So
so we have
instead of
these
using
basic
it in
units,
inches,
right, in the
now
metric
that you
system.
did it with the metric system, your height, right? Is that what you're saying?
System exists because of this.
Right.
So in the metric system, we have these basic units, right? So we have distance, seconds, and so on. And we can put prefixes in front of these in order to give different scales, right? So like one of the most common ones is a K, which is like a kilometer. That means multiply it by 1,000. So Km equals 10 to the third meters. And so that's what I've done on the back here and what I'm doing with this here. So this means 10 picometers, where pico is 10 to the minus 12. And so all you do is sub these
So
things in.
picometer is 10 to the minus 12.
Yeah.
Okay.
Makes sense?
And then the FM is 10 to the minus 15.
Yeah.
And that's common, and that's what you're using here.
Yeah, these are common for chemistry. These are the scale of atoms.
I hold it on metric and look it up and it's the for a year. And did not do that to me. Couldn't find it not crazy, is it? But I would
Okay.
do that. if
So,
you want.
So 35,000 inches would be this, where the electrons would be if I was the center of an atom. So this thing is huge. So the 10 feet scale is way off, right? So that we're many orders of magnitude beyond that. And so if you go through and divide this by 12 and divide it by 5, so dividing by 12 would give you the number of feet, dividing by 5,280 feet would give you the number of miles. So this is about half a mile. So the scale of an atom is that you have this little tiny thing the size of me sitting somewhere, and you have something half a mile out, which is where the electrons cloud, the exterior limit of this electron cloud is, okay? So, yes, so there's some huge size scales here. And if you think about the mass, how the mass is distributed, right? All the mass is in this little tiny part in the center, and the electrons weigh nothing, but they occupy this huge space. And so the next question that you're going to do yourself is, or you can pair up with people, is to take your pen, and I think we have rulers over here, and then what you're going to do is calculate the size of your pen and go through the same process to figure out what the size of a pin-shaped, pin-sized nucleus atom would be. And then we also have one for the solar system. And so hopefully you guys can figure these out. So I have a few slides in here that I put in before I came up with this activity. And so it's just the same idea. So if we had a baseball stadium, the nucleus, if we had this baseball stadium, would just be the size of a marble sitting in the center of it. And so just this size scale, it's awesomely different. And I think it's pretty much inconceivable to think of what an atom actually is. But using these kinds of simple comparisons, these simple allegories, I think they help us get some sort of sense of the scale that's going on in these different systems. And then here's the solar system, but you guys already worked this out on your own, so we'll leave it at that. So, now what we're going to do is talk about how atoms come together and form bonds, and how those bonds lead to molecules, and how we can use that to say something about what these molecules are going to do with each other. Okay? So we already talked about the periodic table, where this comes from, what this means in terms of protons, and also electrons, how it gives us some suggestion about what's going on with electrons. And we already also talked about the noble gases, and how the noble gases kind of occupy this special place on the periodic table where all the elements kind of electronically want to be like the noble gases, right? And so now we're going to expand on this idea a little bit more and see how we can predict or understand bonding in terms of all the atoms wanting to be like noble gases. Okay?
I.e. when other shells fill.
Yes,
Well,
exactly. So, atoms, they're defined in terms of the number of protons. And in order to be neutral, they'll have the same number of electrons as protons. But that's not actually stable, like we just talked about, right? And so we can give them or take away electrons from them in order to make them stable, in order to make them like noble gases. And so if we look at our periodic table down here, I apologize, it's small. But here we have neon, which is the noble gas that's in the second row. And so that has some electronic configuration. So I think it has 10 atoms, or 10 protons in it. So it's going to have 10 electrons in the stable neon. If we go to fluorine, fluorine's going to want to be like neon in order to be stable. So it's going to want to take an electron from somewhere.
So is the goal of an atom to become neutral?
No. So remember, the neutral one would be the one where fluorine has the same number of neutrons, or the same number of protons as electrons.
Yes.
But that's not stable, is what I'm saying. So an individual fluorine will be highly reactive. And it's going to be reactive because it wants to fill the electronic orbitals around it. So it wants one more electron than it has protons to kind of balance out the charge for. And so all of the atoms are going to do something like similar to this, where if you're already in this column, you're happy. Helium is happy, neon is happy, argon is happy. But if you go over one column, fluorine, chlorine, bromine, they all want one more electron so they can be like the noble gases.
So if you have one more electron than proton, you're noble.
No, so if you're noble, you're in this column. You want to electronically be like the noble gases. And so you're going to be taking electrons on.
Okay.
Okay? So, we can also go to the other side of the periodic table and do the exact, or something very similar. So if we go to sodium, say, sodium has one more electron than neon. So sodium can easily give up that electron and then be like neon. Okay? And so this is actually what sodium chloride is, and we're going to talk about this a little bit more in a few slides. But sodium chloride is chloride taking an electron from sodium, sodium giving an electron to chlorine, and then they are both like neon.
Yes.
They're both noble gas-like, because they've traded or given away electrons in this way. And we're going to talk about this a lot more, but that's the core idea here, is that all these atoms, all these elements want to be like the noble gases that are nearest to them, and so they're going to give up or take on electrons in bonding, different kinds of bonding, in order to do that. Okay? And so we've flown through the idea really quickly now, but we're going to go through it a little bit more carefully now, and so hopefully you'll be able to follow what's going on. Okay?
Hopefully.
What was that?
Hopefully.
Hopefully. So, noble gases have filled valence orbitals, and so I'm introducing a new word here, valence. So valence just refers to the number of electrons on the outside, the outermost electrons, okay?
Number of electrons outside of the orbital?
No, the outermost orbitals. So if I go back a slide here, so we have this row here. So this has this row has just hydrogen and helium in it. It's an s orbital. So that's the valence orbital. It's the outermost orbitals.
Oh.
Okay. If I go down one more row, it still has this s orbital, but it's hidden, this one s, but it's hidden inside, and those don't contribute to anything. So now what we have are the electrons that come from this row. So these 8 electrons are the valence orbital. And so as you keep going down, it's all the electrons on that row are the valence electrons. So just the outermost ones. Okay. So valence orbitals are what we're trying to fill. Once we fill them, we become more chemically stable than we were before. And so the noble gases are already inert. They don't react with anything because they're happy. And so other atoms are going to try and get to that same kind of state, same kind of electronic state. Okay? And the way they're going to do that is either by ionizing, so just outright taking or giving up an electron, or by participating in some sort of bond where they can share electrons. And so the periodic table has all this information hidden in it, and all of this stuff comes together to contribute to all of these different properties. We're going to just focus on a few of these, but there's a whole bunch here that you can uncover that we just don't have time to talk about right now. But so what's going to happen is, like I said before, 2 or more atoms can come together. They can either just give up electrons, or they can decide to share electrons in order to reach these different electronic states. And so ionic bonding is what happens, is what we call when one atom gives up an electron to another one. So like that case I described before where sodium and chlorine came together. Sodium gave an electron to chlorine, and it formed an ionic bond. And so that's what table salt is, right? So it's given up an electron, but they still have a strong attraction to each other because of this electrostatic imbalance.
And they stay together to be the molecule.
And they'll stay together just like table salt is a definite substance. You can see that they're holding together in place, and that's what's going on there. So ionic bonding is giving up an electron, and then the strong attraction between the positive and negative ions that form. And then covalent bonding is going to be another case where we have 2 things that come together, but now they're going to share electrons. So neither one of them wants electrons so much that they're going to just pull it away from the other one. They're going to share the electron. And then there's a few different cases of this that we're going to talk about. Okay?
So the giving up can be a giving or taking.
Yeah. And so one useful way to think about these things, to visualize these things, is with something called Lewis dot structures. So Lewis dot structures are where we take the atom we're interested in, so say hydrogen in this case, or fluorine, and we're going to just surround it with the number of valence electrons that it has. And so, for example, hydrogen, it's on the top, in the very top left, right, has 1 electron, so we're going to give it 1 electron here. So that's its 1 valence electron. Fluorine is over in the 7th column, has 7 electrons in its valence shell, so we're going to surround it with 7 little dots.
Does it care which atoms are missing out?
No.
Okay.
This is just purely schematic. These dots represent electrons, but they don't actually represent anywhere in real space.
Got it.
Because remember, the electrons are actually smeared out around this thing. They're not actually localized to
Can
it.
you explain, like, with the left-hand side?
The left
Are you
hand.
going from, yes.
So all I meant by this, so these are meant to be colons, not electrons. So hydrogen,
got it.
we're going to look at the Lewis dot structure of hydrogen. I should have taken out the colon and just left the arrows. Sorry about that.
Okay.
So, hydrogen is represented with 1 electron.
Yeah. And so these are the Lewis dot structures for a single atom of this. This is not a stable state for this to be in, because it wants to fill its valence shells, right? So it's going to want another electron from somewhere. And fluorine is the same way. It's only got 7 here. It wants an 8th one to fill that last place. But we can just, yeah, to put right here. Yeah, to get to the noble gas column. And so we can go through and think about every element in the periodic table and write Lewis dot structures for them. And so this is something I pulled off the internet. And it just goes through the top 20 elements and shows you the dot structure for hydrogen, helium, lithium, and so on. And you can see all it's doing is starting from the top right where you have 1 electron, there's 1 dot. And then you go to helium, there's 2 dots. And then lithium, it's now going to the bottom row, so it now only has 1 valence electron. And it starts from 1, and then it just goes across 2, 3, 4, 5, 6, 7, 8. And then the next row will do the same thing, 1, 2, 3, 4, 5, 6, 7, 8. And so what all these elements are doing when they go through reactions and form bonds is they're going to try to get Lewis dot structures that look like these over here. So 2 hydrogens can come together and form a bond. They'll share 2 electrons and they'll be like a helium. Okay? Hydrogen and fluorine can come together and they can share the 1 electron there in a bond, and then hydrogen will have 2 electrons like this helium, and then fluorine will be sharing that 1 electron and it'll be like neon. So what we're going to be doing is looking at how these things can come together, share electrons, give up electrons, take on electrons, so that they look like these elements over here. Okay?
So depending on who they share with, they're going to look like something else.
Yeah, so each one will have its own characteristic to it. So like hydrogen, it just wants to look like helium, so it's only going to share 1 electron. So even the fluorine has all these other.
Something that only has 1.
That has 1 to share with it. So like fluorine can share this 1 with it.
Oh, it can.
Yeah. And so HF is a dangerous molecule, but it's a molecule that exists. And that forms a very stable bond.
It can
share with anything.
It can share with anything that would give up 1, yeah. So you could have
the lower
methane.
ones can't share.
So the fluorine would share, or what is that, fluoride?
Fluorine?
Fluorine would share because it needs H's to look like
and so
it.
when you come down here, these can still share with lots of other things. So
And
like
they
carbon,
share with no problem?
That's better.
perhaps.
That's a teacher joke.
And we'll keep going. So, maybe just a quick working this out on your own. Can you guys just take one of these elements, or one of these elements, I don't care which one you do, and write down what the Lewis dot structure would be for it? Sure. So say if you did carbon, what would the Lewis dot structure for carbon look like? So carbon is down here on the 2nd row, and then it's 1, 2, 3, 4 over.
Okay.
So we'd have carbon in the middle, and then how many dots would we put around it?
4. No.
Wait.
There would only be 4. I thought it would be 1 plus 2 plus 3 plus.
No.
No. So we're counting. Remember, as we went across, all we did was add 1 electron each time. So lithium gets 1, beryllium gets 2, boron gets 3, carbon gets 4. And if we go down a row to silicon, it's the same thing, because it's right below carbon. It's 1, 2, 3, 4. Okay? So the Lewis dot structure for carbon would be that.
Okay.
Okay? And so if I pick another one, so let's say oxygen, which is on the 2nd row, the same one as carbon now, and as carbon was, and then it's 1, 2, 3, 4, 5, 6 over.
Okay.
Yeah. So oxygen will be 1, 2. Yeah.
Okay. And what about it? What did you say?
What do you mean? So we counted up that it's in the 6th column.
Yeah.
And now I put 6 dots around.
Yeah.
So all we're doing
And
is
2, you always put 2 on the top, and then you start putting more on the side.
It doesn't matter.
Okay, it doesn't matter.
So location doesn't matter, as long as it's
Location doesn't
even.
matter.
As long as it's a
The
number.
only thing to remember with that is that they come in pairs. So we'll put, so I'll put
You
1
have to
in
have
each place by
pairs.
themselves if they can, and then I'll start pairing them up after that.
But you
Okay.
didn't pair the last 2 up.
Here? No.
You don't want to leave
Because they
the
don't want to
side.
be next to each other if they don't have to.
Um,
That's not too important.
okay.
But what's important is that they want to get to that noble gas-like character. So if I have 2 here and 2 open here, it doesn't make a lot of sense for bonding.
Okay.
But you could have 2, like if it wasn't 6 and it was 5, you could have 2 at the
So if
top
we had
and then
nitrogen,
1,
yeah.
1, 1.
Exactly. So if we have nitrogen, it's got 1 lone pair is what we call this, and then it's got 3
Right. Okay.
Okay?
So,
So in essence, you don't want a side by open, by like blank. You kind of don't
Yeah,
want
for
to leave
these
the side
ones,
blank.
just keep in mind that hydrogen will have lots of blank sides because it's only got one dot.
Only got one.
And
Well,
so when it
that's
comes
only one.
along, yeah,
And then
all the rest of them will want to fill its octet, so we'll want to have 8 dots around it.
can you go past
So we do
8 dots?
do we have a?
Not for the ones we're going to talk about. So the transition metals down here, which I said you don't want to talk about in the middle
You
school.
just found a chart.
You can, because now we have these 10 more electrons that come into play. And so you're going to have all kinds of other things that happen. And then you can go down to the actinides, where you then have, what is this, 18 more? No. 10 more, I guess? I don't remember how many there are now. 28. So then you have all these other spots where electrons would go. So these fit into the same kind of ideas, but it just gets a lot more difficult to deal with the accounting.
So are we bonding those two, or what are we doing for carbon and
We're about to
oxygen?
bond.
Okay.
All right. So we know how many electrons these things are bringing to the table. So nitrogen brings 5 electrons, so it's got these 5 dots around it. But like we already talked about, it wants to be like a noble gas. So it's going to try and form bonds. It's going to try and do something in order to fill these 3 empty spots around it. And that's what we're going to talk about now. So I think an easy place to start with this would be to just take a hydrogen, another hydrogen, and an oxygen. Hydrogen, each one of these brings 1 electron with it, right? Oxygen brings, we did it over there, it brings 6 electrons with it. It's got 2 holes here. Each one of these hydrogens has a hole. So we can form bonds between these and form this molecule, which I assume you know what this is, right? Okay. And so the other thing I just want to introduce with this notation is oftentimes when you form a bond, you have the 2 electrons shared between 2 atoms. People will just replace those with lines to signify a bond. So this is the same as this. And sometimes people will get lazy and they'll just start calling these lines too. So you could have this would be the same thing as this. So a line, it represents 2 dots.
Oh.
Okay, so we've seen our first molecule now, right? Where 2 hydrogens can come and form bonds with 1 oxygen, and we can form water. And now what we've done is we've made it so that these 2 hydrogens have electronic configurations around them that are a lot like neon. And this hydrogen has an electronic configuration around it that's a lot like, these are helium. This is neon. And so they've achieved something that looks like the noble gases. Did I get that wrong?
Yeah. You said they were helium.
Helium. So these are helium-like. They have 2 electrons around them.
Helium-like. Okay.
Yeah. And then this is neon-like. It has the 8 electrons around it. All right? That's fine. And that's it. We're going to talk about the nature of these different kinds of bonds coming on, but as we move on. But this is the key to bonding. It's sharing electrons in order to be noble gas-like.
Okay, now you made a big distinction between the ionic and the covalent.
That's coming up.
Okay.
So the bonding, we've covered bonding. There's different kinds of bonds, and we'll talk about that.
And that's how you would write that whole thing for bonding.
Yep. Either one of these is fine.
Well, are they separate, the top and the bottom? I couldn't.
Yeah, these are 2 separate things.
Okay, so the line goes in between after the H?
This line?
Because you're showing it, are you showing 2 different ways? Yes.
Yeah, these are 2 equivalent ways of writing water,
Okay, so
drawing
the
water.
top one, the H, and the hydrogen, and then oxygen is one way, then, okay.
And yeah. So the important thing here is we have hydrogen, oxygen, hydrogen. There's 2 electrons shared between these things.
Okay.
You can rotate this however you want. You can replace the 2 dots with lines, which is what I was doing down here.
Okay.
What's important is you have 2 electrons shared between these, and you have 2 pairs of electrons outside the oxygens that aren't shared with anything.
2 electrons. I see, because the lines are 2 and 2, so there's 6 down there and there's 6 up there. Gotcha. 2 electrons.
8. There. 8, right?
Yes, 8.
All right? I'm still seeing a confused face. So we brought in 8 electrons total. There's 1 with each hydrogen, and there's 6 with the oxygen. They want to be noble gas-like. So they're going to form bonds in order to be like the noble gases. So this oxygen wants 8 electrons like it in order to be like around it, in order to be like neon. So it's going to form bonds with these 2 hydrogens, and now you can count up the electrons. It has 8 per.
And the hydrogen is like the
Helium.
helium.
And so it's going to want 2 electrons around
Got
it. So
it.
it's going to share electrons with
Okay.
oxygen in order to have
Now
those 2
they're all
electrons.
stable.
Yeah. And water is very, very stable. And so we've reached a kind of minima for this, where all of these things are sharing in very favorable ways. Okay? All right, that's the hardest part. Now what we're going to do is look at the way these things share. And this is, I think, conceptually much simpler. So ionic bonding means, all that means is that they're going to form, they're going to share electrons very unfairly. One of them wants electrons a lot, the other one doesn't really want electrons. And so we're going to form a bond around that kind of a strange relationship of one really wanting something and one not really wanting it at all. Okay? What was that? Okay. So, for example, we talked about sodium and chloride before, but sodium fluoride is a similar kind of case. So they both want to achieve neon-like electronic configurations, which means that sodium, if we drew the electronic dot configuration, will want nothing around it. It's going to give up an electron and then have nothing in its valence orbitals. Fluorine, again, is going to want 8 electrons around it, so it's going to want to grab an electron from somewhere, and so that's what's going to happen. Sodium is going to give up an electron and give it to fluorine. And so then we could draw an electronic dot structure for this whole bond, this whole molecule. And so you'd have sodium here with no electrons, and the fluorine here, and they're just attracting each other because we have a positive charge here and a negative charge there. Okay? And so ionic...
Why does Na have a negative charge?
Na has a positive charge.
What has F?
Because it's given up an electron. And I sympathize with you guys. We have to cover a lot of information, so I hope you're able to stick with this. But ionic bonds, the name comes from this fact that we have we have 2 ions here. So it's an ionic bond because we have ions. Okay? And
so if it's a negative and a positive, it's ionic.
Yep. And so here I've just drawn this out a little bit more. So we have a lithium. It goes up and gives up an electron. The fluorine is going to pick up that electron. And so we're going to have, I left out the plus here. So this is lithium plus bonded with fluorine minus. Okay? And then I stole this from the internet somewhere. Just driving this home.
Wikipedia.
Yeah, Wikipedia on the bottom. So you can see we have sodium and fluorine. They would come together. Sodium gives up an electron. Fluorine takes on that electron. And then these things are just attracted to each other like 2 magnets. So that's an ionic bond. Okay? So now we're going to move on and talk about covalent bonds. So covalent bonds, nobody's giving up electrons. We're just going to share electrons with each other. So for example, if we take hydrogen and say 2 hydrogens and bring them together, they both don't want to just be an H with a 1 electron. They want to reach something like helium, right? So they want another electron. And so what they're going to do is share 2 electrons. And so that's how you form a hydrogen molecule. And so whenever you deal with hydrogen, so if we're talking about the hydrogen economy, they're talking about H2 being formed. Because H by itself is not stable. It's going to react with something. And one thing it can react with is another H to form H2. Okay? And there's a lot of molecules like this. I don't know if I go through cases, but like oxygen. Oxygen doesn't just exist as O, it exists as O2 because it wants to share these electrons. Nitrogen, which is a lot of our atmosphere, isn't just 1 nitrogen, it's 2 nitrogens that are sharing electrons in order to reach a more stable state, just like this. Okay? And I guess this mnemonic isn't as useful as ion, ionic, but covalent, they're co-sharing valence electrons, so covalent. There's a little bit more jargon, I think, in that, so it's not quite as useful, but still, it's this idea of sharing, cohabitating, something like that. Okay, so covalent bonds. We can go through and we can do the same thing with, so I already talked about oxygen, where it shares electrons. Hydrogen, or oxygen, or water is the same way, it's sharing electrons. And is there any more points? So now what we're going to do is move on and talk about different cases of covalent bonds. And there's 2 important cases we want to talk about. We want to talk about... Did you have a question?
Is it polar and non-polar?
Yeah.
Oh.
So we're going to talk about polar and non-polar hydrogen bond, or covalent bonds. And the important point here is that non-polar covalent bonds is an even sharing of electrons, and non-polar even. Polar is an uneven sharing of electrons. And you can kind of think of I'm going to keep screwing this up, I apologize. You can kind of think of a polar covalent bond as somewhere in between a pure covalent bond and an ionic bond. So it's going to share electrons somewhat unevenly, but it's still covalent-like. Okay? So covalent is just a word that tells us we're sharing electrons in some way. And so what we want to do is say that in some cases they don't share it perfectly evenly, and that not sharing evenly is important later on when we talk about molecular properties. And we'll talk about it a little bit today, but when you guys start talking about biological molecules, what proteins do in water, this stuff becomes really important. Okay? So, covalent bonds. Like I told you before, there's these two important cases we want to think about. There's the equal sharing. So if you think of two oxygen atoms as tugging on these electrons, if you have a tugging match with yourself, so two oxygen atoms. I really wanted to photograph myself into this, but I didn't come up with time to do that. So if you think about having tug-of-war competition with yourself, you're equally matched, and so no one's going to win that. So it's going to be equal sharing of these electrons. But if you have two different species, and they tug differently, and we're going to quantify that different tugging in a few slides, maybe in the next slide, then you can end up with this non-polar circumstance where it's very uneven. So you can think about having a tug-of-war competition with someone much stronger than yourself. And then we'll end up with this polar covalent bond. Okay? Okay, so this is kind of awkwardly stuck in here. But so we've talked about sharing of electrons, and you can form a bond where two electrons are shared, but you can also form bonds where more than two electrons are shared. And so these are double or triple bonds, and these are important in biology and so on. And so all this means is that, say for example, carbon can come and bond with another carbon, and it can share 4 electrons total. So it'll have 2 lines between it, so it's a double bond. And then you can do the same thing where it's going to share 6 electrons between it, 2 carbons, and so you're going to have a triple bond. And these obviously are, maybe not ethylene so much, but acetylene you're probably pretty familiar with. And so these are very common. And all it means is a double bond means you're sharing 2 sets of electrons or 4 total electrons between them, and so on. Okay? So, I really stuck that in a strange place. But, so distinguishing between different types of bonds. What we now want to do is come up with some way of being able to tell if this is going to be a purely covalent bond, so very even sharing of electrons. It's going to be a polar covalent bond. So, you know, it's mostly covalent, but it's a little bit uneven, or if it's an ionic bond, where one of them is just given up an electron to the other one, okay? So the way we're going to do that is using electronegativity. And so electronegativity is just a measure of the tendency of an atom to want electrons, to pull electrons into itself. And so we can assign electronegativities to every atom in the periodic table, and then when those 2 atoms come together to form a bond, we can look at the difference in their electronegativities to understand whether or not they would form one of these types of bonds. Okay?
That would be expressed numerically.
Yes. And so here are electronegativities. So hydrogen has an electronegativity of 2.1. So this is some number on some arbitrary scale that says hydrogen wants an electron with 2.1 strength. Okay? Helium, it's already in its noble gas state, so it doesn't want electrons, so it doesn't even make sense to talk about an electronegativity for helium. It's happy. But fluorine really wants electrons. So it wants electrons with, I think you can't read this in the back, but it wants electrons with a value of 4 on this scale. And then if we go across, oxygen is 3.5. And you can see that all of the elements have numerical values associated with them. And so like I said before, these numerical values just tell you how much these different elements want electrons. The higher the number, the more it wants electrons. Okay? And so then what we can,
The more it wants what?
electrons. So 4, fluorine is the largest, has the largest electronegativity. It really wants electrons. And then the lowest one would be somewhere down here. Francium, I think is what that is. So it has one of 0.7, so it doesn't really want electrons. And what that actually ends up meaning is that it'll give up its electron really easily. Okay, so then what we can do, like I said before, is we can compare the relative values of these, or we can compare these two, we can compare electronegativities between 2 atoms to understand how they would share electrons in a bond. So for example, we've talked about fluorine and hydrogen quite a bit. When fluorine and hydrogen come together, they share electrons in some way. There's a difference of 1.9 in electronegativity, and so that means that 1.9 will somehow correspond to how polar ionic or non-polar covalent that bond is, and we'll quantify that in the next slide. But so you can see there's just tables you look up, you get all the electronegativities out. Okay, and one thing I briefly mentioned this before, but there's lots of trends that you can extract from the periodic table. And so here we can notice one trend where the electronegativity increases as you go up the periodic table, and it increases as you go across the periodic table. And so these are things that people like to test on them, first of all, but also they're really useful for just understanding the way these different elements would behave and interact with each other, and kind of roughly understand what's going to happen when it's somewhere on the periodic table.
Can you go back one slide for a second?
Of course. Any questions, or did you get what you need? Okay. So, we have electronegativities. Differences in electronegativity are what's important. And so now what we're going to do is look at what those differences actually mean. And so the way this is actually stuck together, or put together, is that what you do is you take, I guess it's on the next slide. So what you do is you take that difference, and if it's 0 to 0.5, it's a non-polar covalent bond. So they're sharing electrons evenly. If it's zero,
what's 0? Oh, the
that
number.
difference in electronegativity. So what we have here is, so for example, lithium fluoride, so LiF here. If you look at that difference in electronegativity, it's a little bit under 3. So a little bit under 3 means it's above 2, so it's an ionic bond. If you look at Cl2, so chlorine, it's the same atom, so it's its own electronegativity minus its own electronegativity. They're going to tug equally on these electrons, so the electronegativity difference will be 0. So that's a covalent bond. And then there's this case in between where you have polar covalent bonds. And so those are in this range right here. So like, for example, we have hydrogen bromide gas. And so this is a strong acid, so there's some uneven sharing, and so you can see the difference is about 1.7, I guess. And so it falls in this range of 0.5 to 2. And so there's these 3 important regimes of bonding that come about when 2 elements come together. And all we do is we look at the electronegativity for each element, we subtract them, so we get the difference between the electronegativity, and that tells us whether these atoms are sharing electrons evenly, or if there's a very uneven sharing going on.
And it's on, the electronegativity is on the periodic table.
It's not usually listed on a normal periodic table.
Oh, it's not on a normal one?
Yeah, but it's in every general chemistry textbook. You would find a periodic table that has this.
That has electronegativity ranges.
Did you mean to say the absolute value of the difference?
Usually, yeah, it's the
Okay.
absolute value. Usually you do the larger one minus the small.
Okay.
But yeah, absolute value.
Yeah, can you go back one slide?
Sure.
Sorry. Or not that one.
This
That one. Okay. So the electronegativity is all the
Yeah.
numbers underneath.
Yeah, so this is not something I would ever expect anyone to just know.
No.
You would give someone a table, you can look up the values.
Okay.
Yep. I guess the one thing I would expect people to know is, if they know a little bit about it, the trends. So it's small down here, large up here. But other than that,
And what did you say about the absolute value?
we're looking at the difference between these two. And so we're going to look at the absolute difference. So so we're going to always do like 4 minus 3.5, and
It's
we're
always
going to
going
take
to
the
be the
absolute
larger
value.
subtracted from the smaller.
Yeah.
The larger subtracted from the smaller.
Or I mean.
The order doesn't matter, we're going to take the
Okay.
absolute value. But if you did the largest one minus the smallest one, you'd always get the absolute
Yeah.
value.
Right.
Okay, so just making this point a little bit more. So we can think about where the electrons are, this cloud around each atom. So ionic bonds would be, these clouds don't really overlap that much. The one with the larger electronegativity, the one that wants electrons more, has pulled the electrons around it. The positive one has given up its electrons, and they stick next to each other because they're like 2 magnets, but they're not actually sharing electrons. The covalent one case means that they're sharing electrons perfectly. So these clouds are going to overlap. So electrons that belong to one will also belong a little bit to the same amount to the other one, and they're sharing evenly. And then the polar covalent is a mixture of these 2 things, where we have the 2 things sharing electrons like a covalent bond, but we also have a little bit of this ionic character, where we have a partial positive charge on one side and a partial negative charge on the other side. So we don't have a full magnet that's developed, but we do have a separation of charge that's occurred, and this is very important. Okay? And so this is how we're going to tie it to molecular properties and things that we kind of observe every day. And so, if you think about the kind of 3 most common phases of matter, so we have gas, liquid, and solid, right? Gas are particles, are molecules that aren't interacting very strongly. So like the noble gases, they're noble gases because they don't interact with anything, they just stay gas. They don't want to even form a liquid because they don't interact strongly enough to want to stick to each other in that kind of arrangement. Water, on the other hand, forms a liquid at a very high temperature if you compare it to other molecules that are the same size as it. And why does it do that? Does anyone know?
Why does water do what?
Why does water form a liquid at room temperature? Why is water a liquid here? Where nitrogen is a similar size, nitrogen is a gas going way down. Carbon dioxide is gas.
To do with the way they're interacting with each other.
Yeah, and so we've already covered it
They're
pretty much.
closer?
Yeah, they're closer because of the way they're interacting, and we've already pretty much covered it because of the kinds of bonds they have. So if we, I guess I should have worked this out here.
Does it have to do with the angle of the, or no?
No, not
I was going
really.
to say size.
So I don't really show it here. I should have. So if we look at this chart here, we can look at the electronegativity of the two atoms in the water molecule, right? So we have oxygen 3.5, hydrogen 2.1. The difference is 1.4. Are you with me?
Yes.
And so if the difference is 1.4, I flipped over it.
bit.
There we go. The difference is 1.4. That means it's a polar covalent bond. So this is a strong bond, but it's also polar. So we've formed, if I flip ahead one more time, a polar covalent bond where we have a partial positive somewhere. So on the hydrogen we have a partial positive. We have a partial negative somewhere else, which is the oxygen in this case because it really wants electrons. So that means that every little water molecule is this uneven sharing of electrons. And so what it ends up doing is forming this little magnet. So water molecules are little magnets floating around that interact with other water molecules. And this characteristic is what makes it so that water is a liquid at room temperature while nitrogen, N2, is not. Because nitrogen evenly shares its electrons, so there's no little magnet that forms. So it's going to remain a gas all the way down to very low temperatures, where water will not. It very quickly wants to interact with other water molecules and form a liquid. Okay? Are you guys with me?
Yeah, so basically you're saying it's because of the electronegativity, or them wanting to bond with one another.
So they want to form with, so oxygen wants to form with hydrogens. The kinds of bonds it forms leads to this charge distribution. That charge distribution leads to life. All right? So, I don't remember how many slides I have left, but let's see. We've covered what I wanted to cover. Okay. So I guess I talked about gas to liquid. So gas are different molecules that really aren't interacting at all. They've reached some point where they don't interact very much. Liquid means that they've started interacting more. So they've condensed down and now they're swimming around each other and they're interacting. And then solid is even stronger interactions. So like ice, as you cool down, you remove kinetic energy, it's able to move less, and so it gets stuck in this potential energy well. Okay? And so you can think of these three things, and obviously temperature is important, the amount of motion you allow the molecules to have is important, but also you can think of these in terms of the strength of interaction between the particles in the system. So water has very strong interactions, so we see liquid and solid phases at relatively low temperatures, or relatively high temperatures, sorry. Whereas for nitrogen, you have to go cool way, way down in order to see it form a liquid. Okay? I'll go until you finish taking notes. All right. And so this is, I think, essentially something I already covered. But noble gases very weakly interact with each other, so they're going to remain gases, noble gases. Polar covalently bonds interact with each other like little magnets, so they're going to interact very strongly. And so we're going to see this strong interaction when we think about melting points, when we think about evaporation points, and so on. And ionic molecules interact even more strongly. And so you're going to see even higher melting points and even higher boiling points. And so if we look at three kind of cases, representative cases of these different situations, O2 is a very even sharing of electrons. It's a covalent bond. It has a very low melting point. Hot water is right in the middle of this polar covalent region. So it's going to be a polar covalent bond. So there's going to be a slight magnet that forms there. They're going to interact pretty strongly. And obviously, and of course, the melting point of water is 0. So right around our kind of daily interaction. But then if we think of a salt, and we could pick almost any salt, but for example, lithium fluoride, these are two actual charges sitting next to each other. They interact very strongly, And so this ends up with a melting point that's very high, 845 degrees Celsius. And so you can use this understanding about the way that two atoms interact to go and then, I mean, we can quantify and measure these things, but we can also just estimate. If you know something is a covalent bond, then it's going to have a very even sharing of electrons, which is going to mean it's not going to interact very strongly with other charged things. And things that are charged are going to interact very strongly with other things that are also charged. And I guess the last thing I had was this kind of brief, goofy review. So what did we learn today? We learned what an atom is, right? And what were the important things that we learned about an atom?
A lot of stuff.
Yeah, all kinds of stuff. This is really goofy, I know. So atoms, why do atoms form bonds? Because they want to share electrons. And then how do these different kinds of bonds affect melting points, or more importantly, just how do they end up extrapolating to these kinds of things that we observe in our everyday life? And so they do that because the way they share electrons leads to these different kinds of bonds. Okay, so that's the end of me lecturing. Now, I hope we have time. Yeah, we have about an hour. So now what you're going to do is I have another activity where what you're going to do is think about a number of different molecules. We're going to look at the way those molecules share electrons, and we're going to build these molecules with marshmallows, and then look at the way different molecules will come together and how they would likely arrange with each other, what interactions would likely be favorable or unfavorable, and so on. Okay? And so hopefully this will make